Okay, so hello and welcome. Here we are, another day, another question. Let's go ahead and continue. Just take a moment to make sure the audio is working. This question is shortest path with alternating colors, LeetCode 1129. Let me pop out the chat. Start with that. Chat out. I think my internet's having a hard time here. Yes, it is. Okay. Sometimes it gets kind of hung up. Yeah, okay. Let's give me a minute here. Okay. There we go. Hopefully the stream is live. How's the OBS doing? Okay, I think we're back. It was a little bit strange. You see, just make sure the audio is working. Hello. It was a little bit strange. Yes. So I'm pretty sure I know what happened. Sometimes my internet is not perfect. It can be a bit spotty. I think it's a software related thing. I actually think it might be malicious software, but I don't really know. I don't know what it is exactly. In any case, let's begin. Let's continue. Shortest path with alternating colors. Companies, you are given an integer n, the number of nodes in a directed graph, where the nodes are labeled from 0 to n-1. Each edge is red or blue in this graph, and there could be self-edges and parallel edges. You're given two arrays, red edges and blue edges, where red edges of I, A sub I, B sub I indicates that there is a directed red edge from node A sub I to node B sub I in the graph, and blue edges of J, U sub J, V sub J indicates that there is a directed blue edge from node U sub J to node V sub J in the graph. Return an array answer of length n, where each answer of x is the length of the shortest path from node 0 to node x, such that the edge colors alternate along the path, or -1 if such a path does not exist. So example 1, n is 3, red edges 0, 1, 1, 2, blue edges are not there, 0, 1, -1. N is 3, different red edges and blue edges, 0, 1, -1 again. N is from 1 and 100, red edges length is 400, blue edges length is 400, most 400. Both of these 0 to 400 inclusive. The lengths of the red edges and the blue edges are both 2. The sizes of these inputs, and A sub I, B sub I, U sub J, V sub J, they're all bounded by n. They're all between 0 and n-1 inclusive. Pretty good number of submissions, decent acceptance rate, kind of on the lower side for so many submissions. So reasonable. So this is like a reasonably challenging medium question, I think. Not too crazy. Okay, let me refresh my chat here, make sure it's working. All right, so let me take a few. So it took me already 4 minutes just to get my internet working and read the question. Let me think about the question for a moment, read it again, try to understand it, and then maybe come up with a solution. See what I can come up with immediately or quickly. See what I can come up with. Number of nodes in a directed graph where the nodes are labeled from 0 to n-1. Okay, nodes in a directed graph. Okay, each edge is red or blue. All right, got it. They describe, okay, an array answer of length n, excuse me, where each answer of I is the length of the shortest path from node 0 to node x, such that the edge colors alternate along the path, or -1 if such a path does not exist. So this kind of makes it think of like a modified Dijkstra's algorithm, which, by the way, the modified Dijkstra's algorithm, it's fastest if you use, of all the implementations, it's like the fastest of the easier solutions, they'll say. Don't use like particularly special data structures. are the ones that use a heap, where you just invalidate nodes in the heap when you process an element. Yeah, and a simple heap is the easiest way to go. And just if you've already invalidated the node, you just drop it, or when you pop it from the heap, you just drop any nodes that have been invalidated. That's like the easiest way to implement. It's a relatively easy way to implement Dijkstra's, and it's faster than trying to do. It's actually faster, both in time to code as well as actual runtime, than to try to implement the, I think it's called the heap down routine, where instead of invalidating a particular node in the heap, you would instead of invalidating it, you would I think move its position in the heap, something to that effect. There's something along those lines. I don't remember exactly how it works, but yeah, I know that Dijkstra's using a heap requires a little bit of extra work. And a very straightforward way of doing it is to just use the set, so you can remove and add elements to the set. I think that's the easiest way, at least in C++. You can do that. However, there's a heap variation that I think is a little bit faster. A little bit more involved to program, not much more, but a little bit more involved. There's actually a good article on it. Actually, I might reference that when I'm coding this here, reference the CPU algorithms website. So anyway, length of the shortest path from 0 to x. Okay. So there's a caveat here. It's not just Dijkstra's. It's also have to alternate the path. So I think I'd want to have the shortest path that starts with a blue edges. I think the idea is I run it twice. The first algorithm, I select only the red edges initially, and the second algorithm, I select only the blue edges initially. I don't think I even need to do it twice. I think I can do it in tandem, just do it simultaneously, where I've got the shortest path starting with red and the shortest path starting with blue, and then those two flip. Then you look for, of the blue paths that are available, of the red path, of all the paths that are available, split them into red and blue. I think it's easier to do it 2 different times. Yeah, let's do it that way. Yeah, let's just do it 2 different times. 2 iterations. Let's try that. So let's do it this way. I'm gonna have color, initial color. Okay. And we're gonna say some more code in there. I have results. Okay. So I want the minimum distance, right? The minimum distance. Let's say this also is going to be, it should be linear in the number of edges, by the way. Technically it would be like E log V, linear in the, not, yeah, it's, yeah, linear rhythmic, sort of in the edges and vertices. Excuse me, but this should be relatively fast. The edges aren't weighted. Oh, no kidding. Oh, it's a lot easier then. Could be self edges and parallel edges. Whoa. Definitely not. Don't need to go backwards though. I think they're not weighted, so we don't need to. You need to use Dijkstra. This is actually a lot easier. It's just simple level order traversal twice is fine. Yeah, 2 level order traversals is fine. So this is actually pretty relatively easy. So let's do result. N is the number of nodes, so it couldn't be more than N. Yeah, I mean, let's do optional. Do optionals too. Or let's do it this way. Just have another int visited. Set that to false. Going a little slow here. So not visited. So actually this should be for each instance. Going to perform a level order traversal. I'm going to update result in each level order traversal. So it's going to start with 0, which is going to be v of 0 equals true. Standard Q, we're going to use Q's. Q dot push 0. It's a double for loop for the level order traversal. Q, it's actually a double while loop really. Not Q empty. Standard Q, next Q, next level. For not Q empty. Move the next Q. Gonna say toggle as well. Toggle starts off at the initial color. There's one more element of this too, which is the adjacency matrix. Empty vectors first, and then also let's do red adjacent and also blue adjacent. Keep this simple, or on the a little bit on the simpler side. So yeah, these aren't weighted, but they could be weighted too. And I think it would be a little more advanced if they were weighted. Vector in the red edges. Redges and bedges. A and B, and these are directed. So these are and the same thing on the other side. Which this could actually just be V0 and V1. Don't need those variables. Maybe save a little bit of memory as we go. Okay. So initially you haven't visited anything. We say we visited the first element with 0. And result of 0 is always just 0. Okay, so now each level we're going to get the front index is going to be q.front. pop that Q. Is it just pop? I think it's just pop. And then we're going to look at each of the neighbors. So depending on toggle, right, we would say if toggle, we're either looking at the red neighbors or the blue neighbors. Right. Actually, even better than that, you can do a reference, right? You can do, maybe a pointer is better. Maybe a pointer is good here. So I can set the pointer to the red adjacency. Auto pointer equals red adjacency. Or of index. And this is going to be adjacent pointer. And if toggle, then set that to the address of the blue adjacency. So the reason for this is, let's say toggle starts off at color 0, which is, we'll just say 0 represents red. And then if toggle is on, then it's blue, right? This is reasonable, I think, to do it this way. And then we can say console to reference adjacency then is the dereference that pointer. All right, so this is really just to have a very simple way of picking between red or blue, because a reference has to be bound to something. So I can't really say const auto adjacent equals red if toggle else adjacent const auto reference adjacent is blue. It's a little bit harder to do it directly that way, so you could just make use of a pointer in between. And then maybe even to make things simple, just set that to the null pointer afterwards. This might be more than it's worth to do this. Like, I feel like this maybe confuses people, you know, like maybe it's not worth doing it this way. I kind of wonder. I'm wondering about this, if this is good or not. I think it's okay. I think it's okay. Anyway, now we're going to find constant neighbor index of adjacency of index, or really just adjacency, actually. Yeah, this doesn't really need to have the index. You could put it here or not. I mean, yeah, doesn't really matter. Either way. So now I have the neighbor index, and I'm going to say if vd of neighbor index not visited, then also after each level, going to toggle. I have to remember to do that. Set it to visited, and now push next queue, push that next index. Okay, so this is a level order traversal. One more detail here is also the count. Int count is 0. This index, we're going to write to result of index equals count, and also increment the count for the next move. Yes. And I think it's okay to do it this way with a visited array because and if they're not met, We'll do -1, it's probably better. Actually, this should not be the count, it should be standard min of, I did this wrong, salt of ix count. Yeah. And this should be n. And then for each result, just a single pass at the end to modify things. So something like this I think works. Let me try to run it. How would I do it on time? 20 minutes? Oh man, compiler. Oh yeah, I forgot to change a variable. Changing a lot of variable names here, or changed, yeah, I refactored the variable without really thinking about it. How would I do it on time? 20 minutes? Compiler. What? Oh. Yeah, I use for loops. I almost never use while loops. I tend to forget that I switch from while loops and for loops back and forth. Okay, let's try a more complicated case. Let's do like n is 5 edges or vertices. Yeah, okay. And we can do 0, 1, 1, 2, 2, 3, 3, 4, 4 and 5. Excuse me. Let's do the same thing over here. Let's do 2, 1, 3, 1. Let's do some random things. 4, 5, 1, 3, 3, 3. Oh, this is interesting. So, oh, this is wrong. I see. I was gonna say, why would self loops be useful? And 1, 2. I don't know. Yeah, I didn't even think about that. Shoot. Okay. I don't have 5. Okay. I did this wrong. I'll come back to it. I think I know what to do, but it's definitely wrong. So the problem is the way that I'm setting up the VD, I'm supposed to alternate colors, right? But the problem is try to explain. It's kind of subtle. That's a pretty easy mistake to make. Actually, let's make a loop. Kind of like this better as a loop, even though it's. So the problem, I think it could be fixed relatively easily with just using the right VD, but the issue is I'll come back to it. I didn't totally complete this here, but I'll come back to it. So the issue is there could be a shorter path that involves, because these are directed edges and they're different color edges, and I'm supposed to be alternating between them. I can get to a point, and it took a red edge to get there, and I'm looking for a blue edge, but let's say there's no blue edges out, except there is a blue edge going back to itself, and there are red edges going out. Well, the algorithm that I wrote just a moment ago would say, hey, there's no way to get out from here, because there's no other blue edge that doesn't bring me right back to where I already was. There's no outbound blue edges. However, in truth, or a different way of looking at it, is that you could take the blue edge to come back and then take one of the red edges to come out. Which means that I shouldn't, the visited points should be color based. In other words, if I got there moving from a red edge, then I shouldn't come back to it with the same, yeah. So if I was moving across a red edge to get to that starting point, or to a particular point, moving across a red edge to get there, I shouldn't move across a red edge again to get there, because then I would be in the same position I was previously, looking for a blue edge, presumably at a later time with a greater amount. So that should just be tossed out. Yeah, so this is a little more sophisticated. It's got to be, so yeah, I assume both colors. No, so actually this is wrong. It's the VD toggle should be true. VD toggle is 0 should be true. Whatever the initial color is, that's the one that, so if the initial color is, let's say 0, right? Then that means I'm looking for red adjacent. Okay. So that means the inbound was blue for red adjacent. So that's what I'm trying to figure out, is whether or not this should be toggle or not toggle, or what this should be exactly. I'm pretty sure it's supposed to be toggle of NIX. I'm trying to explain, trying to say. It could be not toggle here as well. I'm not really sure. I have to think that through a little bit. So let's say, so toggle is going to represent the edge. So this edge is when I get to this neighbor, right? This is the color of the edge that I took to get there. The color of the edge that I took to get there, when toggle is 0, is red, and when it's 1, it's blue. Okay. So the edge that I took to get there was going to be red if it's 0, and blue if, right, so this is the edge, the color that I took to get there. Now, if the initial color is 0, that means the edge that I'm going out from, yeah, so it's actually not toggle here. That's pretty subtle. That's subtle, and that might matter. That's a very subtle thing. Meaning this toggle specifies the outgoing edge, right? So I select an outgoing edge that's red or blue, let's say red, based off of toggle. So toggle would be an outgoing edge. The neighbor is, it's going to record the edge that it took coming in, right? So recording toggle for the edge coming in. But that means that the edge coming in here, since this specifies the edge going out, the edge coming in has to be the opposite. So we assume that the edge coming in is the other color. I realize that's confusing. I realize that's confusing, but that's what it is. Yeah, I have to kind of think that all the way through. Important to think that all the way through, because there's some cases where that could be an issue, and you still generally get the same answer. But let me actually go through those test cases. So a test case where this matters, right, would be, let's say you have 3 nodes, and let's say you have blue edges and red edges. Oh yeah, so the blue edges and red edges, some of them could be empty, some of them could be there or not. There's kind of a lot of variation, but in a situation where, let's say you have 3 nodes, and the first node, it goes out red, and it can come back to itself with red, right? Well, you could start with either color, so I'm not sure if it matters that much, quite frankly. You always can start with either color, but maybe it does matter, because I actually don't think it ever matters, now that I'm thinking about it. I don't know if it ever matters. I mean, the thing that's relevant here is, like, let's say you have 3 nodes, and you're gonna have a red edge from 0 to 1, then you have a red edge from 1 to 2, but you only have a blue edge from 1 to 1, right? So getting from 0 to 3 or 0 to 2, you have to go 0, 1, 1 to 1, 1 to 2, right? My previous algorithm wouldn't handle this properly, I'm sure. Pretty sure it would not. Wrong answer. Okay. -1. All right. So this doesn't handle this one correctly either. Of course. That's awkward. Shoot. That's really awkward, huh? Well, gee. Oh no. No. Oh, you gotta be kidding me. Uh-oh. This might be not toggle. This should be not toggle. So this should work. Excuse me, initial color red. Take a red edge. We go to 1. And we say toggle not of red 1. Set it to true. Push. Go to the next thing. Get a 1. Get the minimum there. We check. So toggle should be looking for blue. So I'm looking for blue edges, right? Toggle is now 1. Look at blue edges. Reach blue edge, which should be 1. Toggle's now blue. And it should return, right? Back to 1. So let me print each of these. I did something wrong here. I'm not entirely sure what it is. It's pretty close though. I think I have the right idea. It's just definitely challenging to get this totally correct. So 0, toggle 0, 1, toggle is 1, 1 is 0, 2 is 1. And then the next iteration we have 0, 1, and that's the end of that. Wait, it worked. I mean, it did what I was expecting. Here, to index 2. It got to index 2. Toggle 1, got there. Should have been 0, 1, 2, 3. Should have been the count. Why didn't this write? What? What? Did I do something wrong? What is going on here? What is going on here? Let's see. What's the problem number? What's up, Rutridge Chintawar? Hello, welcome. Problem number is 1129. 1129. Count is 3. Result of IX is 3. Why did I get a 1? Oh. Oh, okay, I see what I did. Ah, that's a pretty easy mistake to make. Okay, you ready for this? This should be larger. Oh no, that's a subtle thing too. Oh boy, no kidding. No kidding. Whoa. That's a subtle thing too. Look at that. That's really subtle. Oh my goodness. Oh, now they're all wrong. Oh no. Okay, it's probably. Oh man. Whoops. So what I did there was I said, hey, let's pick a sentinel value that's larger than anything else that I could get. And I said, oh, if I'm moving in a breadth first search through a graph, it's not possible for me to move more than n, greater than or equal to, it's more than n, or even n, not possible for me to move more than n minus 1 jumps, visit n minus 1 edges. Not possible for me to visit more than that. So I chose n as a natural sentinel value that's larger than anything else that I can get in the algorithm. Well, after reevaluating and realizing, hey, there are red and blue edges and there are directed edges and there's self edges involved, it is possible to get more than n. In fact, you can get 2n. You could have every node, as you go through it, you visit, so you have a one from one to another, you have red, and then you've got blue, red, blue, red, blue, red, that sort of thing going on. Yeah, in fact, let me actually try that one. That's a good test case to try. Let's do 5, and let's do all of the edges are self edges on blue, and all of the, let's see, 1, 2, 3, 4, and then let's do 0, 1, 1, 2, 2, 3, 3, 4, right? That's a good one to test. So yeah, in that case, you could end up with 2n, I think, right? I think you're gonna have with at most 2n. 2n minus 1. Yeah, that's another thing to check. Is it 2n minus 1 or is it 2n? This is 5 nodes. The last loop, you're not going to do the last loop, I think, once you get there. So yeah, I'm wondering if I should do, and just for good measure, make sure, I'm pretty sure 2n is enough. I'm pretty sure 2n is enough because it seems like the worst case is you just do, basically per vertex, you do 2 hops. And I think it's only the first and last one where you probably wouldn't do 2. Yeah, so I think it's okay to do 2n. I'm gonna go with 2n. I think it's fine. It's a sentinel value. I think it's a reasonable one. And then yeah, at the end, what I had done to get -1 before was that if I reached n, I was flipping that sentinel value back to -1. Reason being, I'm actually going to be running 2 breadth first searches and rewriting over my result value. And so I want to use a large sentinel value that gets written twice, because actually the second iteration that alternates from a different color could visit the same node with a better count. So I want to do 2. These are level order traversals, not just breadth first search traversals. So now also I spent some time trying to figure out whether or not the this initial VD should be not toggle set to true. I don't know if this actually matters. I think I'm okay with setting them both to true initially. And the reason is I don't think it's ever advantageous to return to the initial position from a different color in some kind of a self loop, because you could just start with the other color to begin with, right? So it's always not really that big of a deal, not that advantageous. However, yeah, I don't know. Yeah, it doesn't seem to make sense to me. I don't think you would ever need to come back. Technically, this would be the way to do it, I think, because these actually are kind of represent 2 different, like slightly different things. The toggle here and the toggle here, because this is I'm picking which color that I was outbound, and this is the color that would actually be inbound with respect to that particular value index. Therefore, this should be the color that's inbound to 0. However, toggle is the outbound color, initial outbound color. That's the way to explain it. So it would be not toggle is what you'd want here. I think this is correct. Could be wrong. I'm going to go for it. Yeah, some subtleties here. It was pretty challenging to think it all the way through. It may not be correct too. It may still have a mistake in there somewhere. Oh, got it. Okay, very good. Nice. Took me a while. Got there. Pretty fast too. Almost 100%. All right, I'll submit it 4 more times, and then I'm going to move on to the next question. So that was good. Interesting question. Almost the fastest solution, it seems. Relatively fast solution. Oh, no, not always the fastest, though. 1, 2, 3, 4. We'll go to 5 submissions and pick up the next question. Reasonable solution, though. Not the worst solution it could have been. And what else do I want to say? Yeah, if you like the video, give it a like. 1, 2, 3, 4, one more. And subscribe for more. Subscribe for more videos like this. If you'd like more videos like this, you can subscribe for more. Yeah, I'm trying to think. I'm trying to phrase that in a way where it doesn't sound like a command. If you'd like more of such videos, then you can subscribe, and there will be more. Subscribe for more, I think is fine. Yeah, like the video if you like it. Remember, like the video if you like it. Subscribe for more. I think that's fine. I think that's fine. Yeah, I'm trying to figure out a way to say that without commanding people. But that's probably the best way to say it. All right, I'll stop there. So yeah, I'll reset the stream with another question. That was pretty good. That was pretty good. That was a solid question, challenging. Had to really think about it, and looks like I got it. So not bad.